Xiang from KAIST. Professor Xiang is directs Human Factor and Ergonomics Laboratory at KAIST University. He previously served as KAIST Associate Vice President for International Engagement and was a visiting professor at Purdue University. His research focuses on healthy aging, human-computer interaction, digital human modeling, ergonomic design, and industrial safety, supported by agencies such as NRF, IITP, Samsung Electronics, and Samsung Display. He has published over 130 peer-reviewed papers and serves on editorial boards of leading journals in human factor, ergonomics, and aging. This is my honor to introduce Dr. Xiong, and this is the first webinar of a series of webinars organized by IEA, and we are going to have leading researchers in ergonomics to provide a summary of the recent research activities with our community. The goal of these seminars is to connect the community of Construction Research Congress and also the construction universities across the world with community of IEA, Industrial Ergonomic Association. And we are so honored to host Dr. Xiong for the first webinar of this series. Thank you so much. Dr. Xiong, please, you may start the session.
Okay, so thank you so much, Professor Bezet, Esveni, for your very warm introduction and kind invitation to this remarkable event. And good morning, good evening, and good afternoon, everyone. Thank you all so much for attending today's seminar. My name is Supin Xiong from KAIST, and I'm really honored to be a part of our IEA webinar series as the day speaker. I know from the Professor Bezet, this is the first seminar for our Building and Construction Committee, which I was very honored to be the first speaker for this seminar series. And to take this opportunity, I would like to share some of our recent research progress in advancing construction safety through artificial intelligence and computer vision, focusing on ergonomic risk assessment and real-time monitoring. And this is the outline for today's presentation. I will first provide you a brief research background. Then I will talk about 3 related studies one by one. The first study is real-time PPE compliance monitoring for fall prevention at the construction site. And then the second one is scanner-based multi-person fall detection, consider occlusion. And then the last one is mobile app development for human pose estimation and ergonomic risk assessment. So at the end, I will conclude my talk and also point out the future research directions. By the way, I will reserve at least 10 minutes for your questions and also our discussion at the end of the seminar. Construction has been reported as one of the most hazardous industries, and it is inherently dynamic, complex, and temporary in nature. Therefore, ensure construction safety is very critical, but at the same time is also highly challenging. Let's look at the fatality statistic in construction. Let me utilizing the pointer for the better visualization. So in the US, it has been reported that 1 out of 5 workplace deaths were in construction. And EU also reported similar statistics, around 23%. However, South Korea have much higher work-related deaths was in construction. It was around 4 out of 10. And this also can be reflected as the highest fatality rate among those OECD countries. And in construction, the fatal fall had been constantly reported as the leading cause of the fatalities. So they are falls, struck by, and caught in between, and also concussion. So all these four adding together, they contribute to more than 6% of fatality in construction. And very importantly is that the four has been the biggest contributor. It serves alone account for 36% of the total fatality in construction. Therefore, preventing fall and fall-related injuries in construction is very crucial to ensure construction safety. Besides fatal injuries, we also need to consider non-fatal injuries, especially the work-related muscle scan disorders. So a report from Canada has showed that construction also highly associated with the largest or highest prevalence rate of work-related muscle scan disorders among all the other industries. If we look at the different countries, different regions, we can find out that in US, like 30% of all non-fatality occupation injuries were work-related muscle scan disorders. And EU, based on the self-reported studies, they have found that 6% of workers have self-reported work-related muscle scan disorders. In South Korea, each year, that's around 10,000 compensated cases are from work-related muscle scan disorders. Most of those cases are in manufacturing, construction, and transport. Well, in the low medium income countries such as Pakistan and also Sri Lanka, so the work-related muscle scan disorders among construction workers are even higher. So you can say that the prevalence rate is more than 80%. So therefore, aside from the fall and injury prevention, we also need to consider the regular ergonomic risk assessment to minimizing the work-related muscle scan disorders in construction. So putting those annoying statistic data together, we can find out that construction industry itself is a highly risk. That has 20 to 40% of workplace deaths associated with very high rate of fall and work-related muscle scan disorders. So therefore, there's an urgent need of innovative solution to improve the current situations. And in this direction, we believe the computer vision and artificial intelligence can come in and play a very important role. This is because computer vision, they can continuously track the construction site and also work behavior in real time in a low cost and non-invasive manner. And artificial intelligence can support automatically the object detection, like data analytics, and also intelligent inference. So integration these two technologies, they could help us to develop automated, real-time, and scalable safety solutions. So in line with this, we performed like three research studies. So the first research studies is focused on the PPE compliance monitoring for fall prevention. The key idea is that we continuously monitoring the work's behavior, what they will like required personal protection equipment when they're working at high levels. For example, safety helmet, harness, and lanyard or lifeline are probably not. If they don't, so our system will real-time recognize those risk behavior and then inform the safety manager so that they can correct the risk behavior to prevent the fall incidents. The second study is that in case the fall accident happens, how to reliably to detect the fall accidents and send the immediate alarm to the safety team or to the medical care team so that they can providing the workers who suffer from the fall accidents the immediately medical help. In this case, we can reducing the fall-related injuries, especially the fall fatalities. The third study is more with work-related muscle scan disorders. So we developed a mobile application so that they can utilize computer vision to estimate human pulse and then based on the post to perform automated ergonomic risk assessment. So in this case, we can identify the risk jobs associated with the high work-related muscle skeletal disorders earlier, so that we can redesign the jobs, or we can do the interventions to minimizing the prevalence of work-related muscle skeletal disorders in construction. So now I'm going to introduce those studies one by one. So the first study is real-time PPE compliance monitoring for fall prevention. This study had been published last year in Journal of Construction Engineering and Management. So since the most of the contents I talk here had been published, so here I will skip most of the technical details. Instead, I will focus on the overall research methodology and also the key research findings, so for you have a better overall understanding. So here is the overall research framework we use for develop such system. So first one, we built a large data set, customized data set for different kind of PPE at the construction site. And then we develop a object detection model, which is a UNO-weighted model to detect those PPE compliance accurately and robust. And then we deploy this object detection model in the portable edge device, so that we can, based on the real-time video input, we can real-time monitoring the PPE compliance. So that is basically the overall research methodology we use. And now I want to give a little bit details about each of the key steps. So for data set construction, we built the data set from 5 different sources. So the first one is public data set, like RoboFlow and also Air Harbor. Those public data set that has the PPE usage information in the various kind of construction scenarios. And we also are getting the field data set from the construction project at our campus. And also we search the website to get the construction image together with the PPE information. And also our students also utilize a handheld camera to capture the various kind of like a construction like an image, especially when the workers utilizing or don't utilizing the personal protection equipment. And the last one is that we also, to take care of some of the class, for example, like 9-yard or lifeline, it's very real cases and very small objects. So we also build like this kind of synthetic image so that we can balance the classes. So overall, we have built a large representative PPE data set, which you can say that the total image we have is 11,000 image. And after that, the data set, construction, we also need to enable the class, for example, the PPE, right? Helmet, harness, lifeline, and also when the workers, they don't wear the helmet or harness, we also need to label out so that in case they don't wear those PPE properly, we can detect it. And then for the class of the instance in each class, you can say that most of them has more than 7,000 of the instance for each class. However, for the lifeline or 9-yard, the number is relatively smaller. Okay, so that is also, but it's also more than 3,000. And for the object detection, we're utilizing state-of-art model, which is called UNO. You only look at once. The basic idea is that this model, they can detect the bounding box and at the same time inference inside the bounding box what are the class belongs to. So for example, in this image, they can detect, in this case, this is the dog and then bicycle and the car simultaneously. So we utilize this kind of UNO model is to ensure the real-time performance, because this is one state detector. So in that sense, we can perform the real-time monitoring for different PPE classes. So even though we're trying to utilizing the state-of-art model for as our object detection model, we do need to improve the current model, because for our case is that like a PP detection, especially for the 9-yard and the lifeline, those are very thin and small objects, and then they have to be detected accurately within the complex background. So in this case, we have to remodify the backbone of the unit model. In this case, we add in this kind of attention model so that they are selectively pay more attention to the PPE which attached it to the human body. And at the same time, the second challenge is that we have to balance the accuracy, classification accuracy, or detection accuracy with the computation resources. Because our idea is that we want to make sure our model can be applied in the edge device, so that we can place this kind of system in any of the temporary construction site. So in that sense, we have to make the model itself is lightweight. So in this sense, what we did is that we modified the neck part of the unit model and add ghost mode, so that it can make the model itself is lightweight, but at the same time the balance can be ensured. Okay, so we do make some other improvements, but here I only want to talk a little bit more about those two key improvements. So after we build a model, we need to evaluate how good is our model. So here we're utilizing average processing and also the mean average processing, because this is involving multiple class, right? It's not just 2 class. So here is the model performance. You can see that we compare our model, proposed model, with the state-of-art model, which typically utilizing in the object detection. You can see our model, they achieve the highest accuracy for all these 5 classes. And the overall accuracy is over than 92.5. And aside from the accuracy, we also need to consider the size and the real-time performance of our model. So very important metrics is FPS, which is a frame per second. So frame per second, in this case, in general, for the real-time monitoring performance, we have to reach 5 frames per second, which in that sense, you can say the real-time monitoring performance is good. So for our model, you can say after we modify the model, the structure, you can say the model size becomes somewhat reasonable, and then the real-time performance is very good. It's like 9 frames per second. So that in that sense, this shows that our proposed model, they can enhance the accuracy, but at the same time can keep the model itself is lightweighted. And this shows the results before and after we apply the attention model. You can see that before apply the attention model, so the model, they put a lot of attention on the background information instead of the workers and also the attachments, like PP attachment. So after we apply the attention model, you can see that, so the model, the artificial intelligence model, they mainly look at the workers together with the PP attachment. So in that sense, we can say they can improve the PPE detection accuracy. And here is some of the detection results. I utilize the image as examples. So for most of the case, of course, it's true case, because we have around 92.5% of the accuracy. So you can say that if they don't wear the helmet and harness, they will be able to detect it. If they wear it, they can also detect accurately. And in the simple background, if there has a complicated background, single person, and if there's a multiple person in the very complicated background as well as a far distance, so the model can detect the personal protection equipment appropriately and accurately. However, we also found out they had some of the wrong detection cases. So especially about the 9-yard, which is lifeline. Lifeline is that you can say these workers, they wore the lifeline, but the model doesn't detect successfully. So that in general, we found that this is this could be the wrong cases, because the 9-yard and lifeline is very thin compared with the background. And this is also the same in the cases. They wear the lifeline but don't detect successfully. However, sometimes background, you can see here, this background they detect as lifeline, but in fact it's not lifeline. So in that sense, you can say that this is the misclassify the background information as lifeline. So in general, we found out that for the lifeline detection is not as reliable, as accurate as harmonies and lifeline. And that's why I say in the Harmonies and Hammett. So that's in the future direction, we need further improve our model in terms of this kind of like a lifeline detection. And if they don't work the lifeline, so that we can find it out and then inform the safety manager about this kind of risk behavior. So we also collaborated with our industry partner to do a small-scale field test. This one, let me show you the small demo video. So that is two people working together to do the construction work, and then you can see that all this personal protective equipment, if they work, they successfully detect it. And even there are some occlusion cases, so they have to be detected successfully. However, if they don't work it, the system will pop up the non-message. So later I will show another testing video that is at the end of this like two studies, because we're going to combine the personal protection equipment detection as well as the fault detection together in our portable system. So I think we briefly talk about how we develop a system for real-time PPE compliance monitoring for fault prevention. So now I'm going to move to another one, which is skeleton-based multi-person fault detection. So this study has been published recently in automation in construction. The major contribution of this paper is that we consider the multi-person in the construction site, and also we consider occlusion cases. So construction site typically has occlusion cases. So how to build a robust model. So here we're utilizing skeleton-based model for the fault detection. So this is the overall research methodology we use for fault detection. You can see that here we first based on the video input, and then we detect the person. And at the same time, we have to continue tracking about the person if there's multiple person. For example, this is the first person, this is the second person. So we need we develop some algorithm which called sort algorithm to tracing the person. So make sure, even though, for example, some slides or some frames, they're missing the skeleton information of that person, but later they can still match with the right person. And then after that, we're utilizing alpha poles to extract the skeleton of each of the person. And at the same time, based on the sequence of the skeleton, we're utilizing a hybrid deep learning model to classify whether the workers itself is doing the normal working activity or is experienced the full accidents. That is the overall like a flowchart for our methodology. So here again, we need to first, refine the data set, because previously it's mainly for PPE detection, but here we have to detect the full accidents. So here we have to first add in the person as an additional class. At the same time, we also need to add in the additional image to including the full accidents cases. So here we have 3 data sets we use to include the full accidents cases. So AHub dataset, this dataset is a very nice dataset from construction site. And the K4 dataset, they have 4 incidents, which is built from our lab. It's simulating the 4 accidents. And the multi-camera dataset itself is the 4 ways captured by the multi-view of the camera. So we utilize these 3 datasets to ensure that has the 4 incidents. So here you can see that, very important thing that when, as I mentioned, when multiple workers working together, we have to ensure we can continue tracking about each of the individual workers. So we're utilizing simple online and real-time tracking algorithm. The major concept is that based on the previous frame and the bounding box, then we utilize the common filter to estimate the next frame. So what is the bounding box it is? And then we compare the estimated bounding box with the current frame, the detected bounding box. And then we, based on this algorithm, like Hungary algorithm, so we can know, for example, whether this box or this person, they are the same person. So that basically is how we tracing the different person. And then after we be able to detect different person and tracing different person, then we utilize alpha poles to extract the skeleton information. You can see this one, we're getting 13 key points from the detected human. You can say that is the different workers, and then we can detect their skeleton. So then we, based on the setting skeleton points and based on sequence of the skeleton, then we developed hybrid deep learning algorithm. So here we first go through the convolution layers to extract the spatial relationship among those key points. And then we further put in those feature maps into non-shortened memory so that we can capture about temporal dynamics. So that for 4 is very important. 4 important basically because in the skeleton orientation, they could have changes, right? So that's a combination of the spatial relationship with temporal relationship that can help us to do the accurate detection of the 4. At the same time, they can maintain the fast inference rate. So we're utilizing skeleton information because skeleton information is more representative for human body pose. So in that sense, the detection of the 4 is more robust, even with some part of occlusion. Later we'll demonstrate it. So to evaluate the model performance, we're utilizing the 3 metrics: accuracy, sensitivity, specificity, because this is binary class. Binary class, that means we only have 2 classes, 4 and non-4, right? So in that sense, we can utilize accuracy, sensitivity, specificity. Sensitivity is that how accurate our model can detect the 4 when the 4 accident happens. And the specificity is that when the workers performing normal work activity, so what our model don't wrongly classify then as the 4 accidents. So in that sense, it's about force or not, minimize the force or not. Okay, so here is that we compare our algorithm, hybrid deep learning algorithm, together with typically the like a 4 detection algorithm based on the skeleton. So you can say that again, the algorithm we proposed algorithm-wise, the accuracy, they are very close to the current state art of algorithm, like STGCN, and better than the other 2 type of algorithm. And the advantage of our algorithm is that they also has fast, like a frame per second. That means the real-time performance is pretty good. So overall accuracy, you can say that it's comparable and even higher. And then we can ensure also real-time performance. Another big advantage our algorithm had is that they are performed relatively robust, even with occlusion cases. So here we, based on the image, we classify the occlusion level in terms of the low occlusion and the high occlusion, and then we check about the overall performance of our algorithm under the different occlusion level. So you can say that, so when the occlusion level is low, which is shown in the first bar, so both sensitivity, specificity are all very high, right? So around 96, more than 96, 99. So overall is 98.7. So for the higher occlusion cases, sensitivity even higher, getting higher, but specifically they do drop significantly. So this one, in fact, is somewhat reasonable because here, specificity is no means that when there has high occlusion cases, that means the human body or worker's body has been highly occluded. So in this case, our system, our model could be intended to classify this one as, even though there's like a working activity that will intended to classify as the 4 accidents. So even though this is one classification, however, if we look at our data in the construction side, so the high occlusion cases in general, they are highly associated with the 4 accidents. So that's why the model itself, when they trained, they were intended to classify as a 4, right? Because typically you say like 4 down, then some of the joints cannot be seen by the camera. So, but overall, if you look at here, you can say overall the accuracy is very high, which means that most of the case for high occlusion cases is the 4 accidents. So in fact, even though the specificity is low, that doesn't influence too much about overall accuracy. So that is how, say to show the model itself is somewhat robust to the different occlusion level. And here we define the occlusion utilizing the the missing key joints together with the surface area. So we define the occlusion level a little bit more scientifically utilizing the method we propose. So after we develop the fault detection model, we want to deploy the system to the portable construction site. So that means even the construction site is temporal, and then we can put in our system in any of the construction site, and then we'll continue to monitor their like a PPE compliance as well as the fault detection. So here is the overall design of our system. You can see that here we're utilizing the webcam and then the tripod so that we can put in the system in any of the construction site, and then our like established or developed model, AI model was put in the edge device. And then based on the video input, so this one will continuously inference or detect whether the people wear the personal protective equipment or not. If they are not, then they will send the safety alert to the safety management team so that they can correct the behavior, risk behavior workers. On the other side, if the fault action happens, and then this fault detection model will send the alarm message to the safety control team as well as the medical team so that they can provide in the immediate help for the workers for experienced fault accidents. So this is the overall design. So detailed design here, we're utilizing like a regular webcam with tripod for the portability, and edge device, which is don't need very high like GPU performance, and also portable monitoring for visualizing the results. And this one, you can see that we can put in this kind of system to the different construction site, and they can continuously monitoring the works behavior together with their the fault accidents if it happens. So let me show you the demo of the system we developed. So this is, I think, the prototype system we have developed, and we can place in the construction site. And then this one shows they're continuous monitoring the two workers, and then whether they wear the personal protective equipment. If there's no, you can see here, they will put in the non-message. And in case the fault accident happens, they're also going to pop up the a non-message. And they can detect the fault in the occlusion cases, without occlusion cases. And even when we use skeleton, we found out that even the nighting condition is very low nightness. So the system can also reliably detect the fault accidents because that we utilize the skeleton-based detection model. So that is about the system, portable system we have been developed. And now I'm going to move further to talk about a mobile app we have been developed for human pose estimation and ergonomic risk assessment. So part of the research has been published in International Journal of Industrial Economics, but later on we further improved the system to develop a mobile app so that we can directly translate our research into the practice. So that is like this year we developed a mobile app. So here we have a different computer vision-based 3D pose estimation model we could use for mobile app development. So one of the widely utilizing open source model is MLPose. Another one is medium pipe. So MLPose, the concept for 3D pose estimation is as follows. So based on the image, then they first detect the person, and then they, based on detect the person, they extract the 2D pose. And then they, based on the pose lifting algorithm, they lifting the 2D pose to 3D pose estimation. So that is like a top-down approach. You can say like top-down, detect the person first, then 2D pose, then 3D pose. And medium pipe on the other side is a little bit different approach. So what they use is that first detect the person, and then they will first detect the face. Face typically is like very mature technology now. We detect the face, and with the key points of face, then they utilize in lightweight CNN model to inference the rest of the key points. And then later on utilizing a regression model to estimate 3D pose. So that is they utilize different modeling approach. But for us, what we're really interested about is that which pose estimation model is more accurate to provide us the pose information. And secondly, which one they are easier for us to implement to develop mobile app. So this is our research questions. What are we interested? So first one is the which pose estimation method they provide us the more accurate results in terms of the human pose estimation. And at the same time, we're also interested about what kind of camera configuration, so camera angle we should use so that we can provide in the highest accuracy. So this is more about like the input of the pose information from the computer vision. The second one is that once we get, say, the human pose information, then how to do the automated ergonomic risk assessment so that we can ensure the risk assessment results is reliable and also it's interpretable. And lastly, we want to know whether we can develop a mobile application based on computer vision so that we can perform automated ergonomic risk assessment. So those are the three questions we are interested to investigate it. And to look at those questions, we first establish this kind of test setup. So test setup is that you can say we put in this kind of audit track high-speed camera, which is ensure we can capture if the people and workers performing their different activity here, we can capture their motions and also posture accurately. So this serves as the ground truth for human pose. And then at the same time, we put three smartphone here. You can say that a different orientation. So for example, located in front of the workers or at the side of workers or at 45 degree. So we're testing different camera placement to ensure whether the camera placement influence the pose estimation accuracy, and also if yes, which camera position, camera angle we should use for accurate pose estimation. So this camera will capture the video, and then later on we utilize computer vision based technology to estimate the 3D pose from the captured video. So here is the demo video to show how we can get golden reference motion capture data. So we're utilizing audit track. You can say that we're putting the landmarks on the body, and then based on the high-speed camera, we can capture the trajectory of the human each joint movements and also their pose information. So this is the serve as ground truth value for evaluate the different pose estimation method. And we also tested the accuracy under the different task scenario. For example, static task with occlusion or without occlusion, and dynamic task again, with occlusion, without occlusion cases. So we're trying to mimic typical tasks performed in the construction site, like lifting, like a transport, and also climb to the ladder, or performing assembling, or some of the working behind the obstacles or blocking by the wall and so on. So that basically, we're trying to mimic some of the typical features in the construction site. So for the evaluation of which method provide us the better pose estimation results, so we're utilizing joint position error as well as joint angle error as evaluation metrics. So those has been defined as the difference with ground truth value. Ground truth value I mentioned previously, we get the ground truth is from the high-speed camera. And here is the novel results. It shows that the computer vision based pose estimation method, camera angle, and also the different tasks that do influence the joint position error as well as the joint angle error. So here I will skip the details. Instead, I want to show you the key findings we get from these studies. So if you look at the joint position error crossing the different computer vision based pose estimation method, you can find out that the medium pipe that has a significantly lower joint position error as well as joint angle error compared with the ML pose. However, you can see both methods, in fact, they can achieve somewhat reasonable accuracy. In terms of a joint angle, you can say medium pipe average joint angle error is around like 11 degree. However, animal pose is also around like 15 degree. It's not, I think in general, overall, you can say the performance-wise, not that bad. So, however, of course, medium pipe is, significantly better in terms of statistic significance, better than the like animal pose. So basically, if we look at the accuracy, we want to recommend 3D pose estimation method is medium pipe. And also we look at different tasks, so how they influence the joint position error and the joint angle error. You can say that overall, when the people working with obstacles, that means they get blocked it. Part of their body get blocked it. You can say the estimation error has been significantly higher than the other task. And that highlighted that higher accuracy level lead to higher post-estimation error in general. And another important thing, we have to also find out the ideal camera placement and camera angle for the post-estimation. So in terms of joint position, you can say that we found out that the side view, when we putting the camera on the side, they show significantly higher joint position error compared with front view and also 45 degree. And for the joint angle error, so the front view, they show significantly higher joint angle error compared with the side and the 45 degree. So if we putting this together, you want to get a minimized joint angle and joint position. So here you can say that the 45 degree angle, the camera placement is the best. So it's idea, the placement. So now we know which computer vision based post estimation method we should use, and also what kind of a camera placement we should apply. Then next step is that we're utilizing the post information estimated from the model we develop, and then we can automate the ergonomic risk assessment. So here we mainly focus on the two wide neural net tools. One is Luna, another one is Reba. So Luna, I think most of you may know, right? If you're working in the human factors and ergonomics field. So Luna is basically look at the rapid up NIP assessment. So based on the post score, we're adding the node information, we're adding the muscle usage information, then we can get the Luna score from 1 to 7. And then we can further classify into 4 different risk levels. And the REBA score, REBA is the entire body assessment. So again, there's a post information, then the node information, and then adding together, they are from 1 to 15 score, and then they can classify into 5 different risk levels. So those are typically the method we utilize for ergonomic risk assessment. But in general, those methods are based on the observation, right? Professionals, they observe the workers, how they perform it, and then they judge the angle, posture, durations, and then they put in each score, and then later on they add in together, right? So that is, I think, typically how they performing this kind of ergonomic risk assessment. But for us, our idea is that we should do this automatically and accurately, because we can get in the post estimation very accurately from computer vision based technology. And at the same time, those calculations, we can automate it, those calculations, so that, we can, the people without too much economics professional knowledge, they can also understand, the risk. They can also perform those evaluation very quickly. So to performing the ergonomic risk assessment, we need to define the 3 ergonomic plan scientifically, so that we can evaluate the post duration from different plans. For example, here we define the sagittal plan, like a corolla plan, and also the transverse plan. And based on these 3 different ergonomic plan, we can evaluate the post duration from neutral posture. For example, in this case, the trunk, for example, trunk flexion from sagittal plan, and then side bending from corolla plan, and also the twisting from this transverse plan. So once we have this kind of pose duration from each of the neutral posture, then we can evaluate the associated risk more accurately. So based on the pose data we get from previous calculation and also the computer vision based knowledge, and then we can calculate the Luna and Reba score automatically. And we also need to evaluate how good is our automatic calculation compared with the ground truth value. So here we found out that the absolute agreement between the computer vision based Luna and Reba score, you can say that it's very close to the ground truth. So ICC, that is the intra-class correlation itself is 0.9. Why is the perfect agreement? So it's identify the excellent reliability, and median pi with the Reba tool is good reliability. So overall, this shows that computer vision, they can provide us very reliable economic risk assessment, at least for Luna and Reba tools. And then we further want to translate the research we have performed before into the practice. So that's why we are trying to develop a mobile app, which is everyone, they can take the photos, take the videos, utilizing their smartphone, and then they can perform those economic risk assessment very quickly. So this is the major user interface. You can say that the people can choosing which economic risk assessment tools they're going to use. Here we demonstrate the Luna and Reba. Later, we're going to add in more economic risk assessment tools in this mobile application. And at the same time, they can load their per-recorded video or real-time recorded video to for the economic risk assessment. So this is the major user interface to demonstrate the key function of our mobile app. So noted the video, and then this one shows the overall the score of Luna and Reba, and also the corresponding risk level. And at the same time, they also show for the entire work activity. So what proportion of the time spent in the risk level or safe level. And also it shows the dynamics of changes of the Luna and Reba score. Okay, so and over the time. So in that sense, we can find out well the problems comes out, right? So that we can improve the job later on. So the bottom part here is also that has associated risk level. For Reba, as I mentioned, we have 5 different risk levels. So this one also have the 9 to identify different risk level. And for Reba, it's going to be 4. So that is the dynamic visualization about the distribution of the risk level along the time. And the bottom is for easy navigation. So overall assessment and each part of body as well as the detailed information. So aside from the overall risk assessment, our mobile application also providing the detailed investigation on each of the joints. So what the risk level associated with each of the joints, so that we could know, for example, work-related muscular disorders, which part of body. And at the same time, they providing automatic suggestions. So what are the issues? For example, this trunk has the high risk. What are the reasons causing the high risk? And then what are suggestions to avoid this kind of high risk on the trunk? And also, for example, providing some of the like a reasonable range or safe range for each of the joints based on the statistical data. So now let me demonstrate the function of our developed mobile application. So first, you can say that people choosing the which type of tools they use, and then they know the recorded video. And after that, the system start to processing the post estimation and also calculate the score. You can say this is the overall score and risk level, and then distribution, as well as the detailed of each joint, what are risk level, and along the time as well. So that basically, they're also providing the suggestions for each part of body. For example, if it has high risk, and then how to avoid general guidance. Okay, so that is about our mobile phone, mobile app development. So now I think I'm utilizing almost 50 minutes. So now I should conclude my talk. So the construction industry itself is inherent high risk, lead to both fatal and non-fatal injury, especially the four fatalities and also work-related muscle scan disorders. And we believe the recent advance in artificial intelligence and computer vision, they hold great potential for developing innovative technology that can transform the construction safety management. So in line with this direction, we have developed computer vision-based artificial intelligence system for fall prevention, accidents unknown, and ergonomic risk assessment. So mainly contribution is that we develop portable PPE compliance monitoring system to prevent fall, and we also develop robust skeleton-based multi-person fall detection, consider occlusion, and also develop a computer vision-based mobile app for automated work-related muscle scan disorders assessment. And looking forward, we still need to further improve the system and the technology will be developed in terms of, for example, integration multi-camera view for addressing the occlusion issue, or integration computer vision with wearables to address occlusion. Another direction we're going to work in further is that to add like a more biomechanics model for comprehensive ergonomic assessment. Currently, we mainly focus on Luna and Reba, but in the future, we will also consider no back compression force based on the 3D pose information to evaluate the no back risk. And also very important thing is that we have to expand the data set to include diverse construction scenario. So current data set, even though it's representative, is custom built, but we believe if we build even larger data set to have more diverse construction scenario, our model will be more robust and more accurate. And also very important thing that we have to collaboration with our industry collaborators to do the field test to promote real world application in construction site. And one of the final note is that we also think it's very important to go beyond technology itself to promote integrated approach for construction safety. For example, to foster safety first culture, training the workers, and also make sure the safety program is accountable and promote community engagement for safety program. So here is major reference I use for this talk, and more of technical details. I think if you're interested, you can reference those publications. And I also want to acknowledge the funding support from this study and also the hard work from our research team members. So especially the first three members, their research work highly contribute to today's talk. Finally, I want to take one moment to promote the journal I'm serving as editor and editor board members. I warmly welcome all of you to submit interesting work and high quality research to those good quality journal in the field of human factors and economics. So that's basically the end of my presentation. Thank you very much. Now I'm happy to take any questions, suggestions if you have. Thank you.
Thank you so much, Dr. Cheung. A big round of applause for the wonderful presentation you provided. I think this was a very well-rounded research talk. You talk about the theory, you used sophisticated data analytic techniques, and also you delivered mobile applications that can be used in the industry. So it was a research from the inception of the idea to the practice, and that was wonderful. Really appreciate it. So we have time for a couple of short questions from the audience. Before we go to the audience, I just have a short question from myself to start the Q&A. Dr. Cheung, how do you deal with the privacy issue? The system looks great in detecting potential lack of PPE and also fall, but sometimes workers may not like to be recorded. And also the data collected might be used in the court too if an accident happens, so perhaps can put the blame on the workers or maybe remove the blame, but it might create some privacy issue. How do you deal with those challenges?
In fact, this is very, very good questions and also challenge questions. We currently we didn't, put in those privacy as the into the good considerations, because this one is that based on the regulation. For example, like certain industry, if they want to build a construction project, they do need the continuous monitoring. They have a CCTV camera. They anyway, the workers, if you go to that construction site, you will be monitored. So of course, our system is that we will not put in like a cloud server. Instead, we just put in like say portable like local like a edge device. So only the permitted safety manager they can access those informations. And once the accidents was detected or PPE was not well cases, they will capture the screen, and the screen will send it to the safety manager, and then only the permitted person can access those information. All the others they will not be able to. So that is something we think about. Can partially address the the privacy issue. However, I do agree with you. I think later on, if we want to have like for example like large scale implementation, so we may need to say utilize some mask information, mask their face information, so that we can detect the problem, but at the same time to keep their privacy. Yes. Very good questions. Thank you.
Thank you so much. Thank you for a great explanation. For audience, if you have any question, if you can raise your hand electronically, I will read the names and then you can open your mic and ask the question. Thank you so much.
Behzad, do you hear
yes,
me?
This is Azamal. Yes, I can hear you. Please go ahead, and then we go to Yibo.
Thank you. I'm sorry, I couldn't find the button where I raised my hand.
It's totally fine. Thank you so much. Please go ahead.
Good to see you, by the way. It's been a while since we talked.
Yeah, me too. Very nice to thank you so much for attending.
Thank you. This is Zaman. Right now I'm engaged in some capacity of research related to safety, but also I'm heavily engaged in the industry. I'm a vice president of a consulting company, and we interact with construction and project on daily basis. And I want to stress actually what Behzad actually brought to the table, because yesterday I was in a big executive meeting where similar intervention was considered, and one of the executive kind of vetoed that and said, we have to look at our workers as people, as not robots, which is kind of like a little bit of like very harsh comment actually. But one of the things that actually I noticed doing almost 6 months of behavior observation, safety behavior observation with workers really do not like to be filmed, not just for privacy issues. It's just in general, it introduced so much bias, and it's a problem, as a researcher. You think like from our perspective, we're trying to provide a tool to keep you safe, right? But it is sometimes very hard actually to make that argument with someone who has quote unquote an old school mindset and say, I've been doing this job for 30 years. You don't need like to, I know how to do my job, or like, this is not going to make a difference in my safety, especially when our other factors. So that one issue actually is still very significant. And I'm giving you kind of the industry view on this, not just the academic view on it. The second thing, I don't know if I missed it, or you actually may say that, but I would say one of the suggestions I would have for this research is for the position recognition. Do you think it would help if we add some tags on specific joints of the body? Let's say that a worker is putting a vest on or a shirt on, and we would have, let's say green tags or labels for the elbows, red tabs or labels for the hands, and maybe for the knees. Does that make an improvement for the positioning recognition and make it easy, at least for the camera, even in dark environment, to recognize those where lighting is not great?
Okay, I think Man, thank you very much for your, the suggestions, comments. I think the first comment you talk about is like a privacy and also technology acceptance, right, by the workers.
Yeah.
So I think that's a very, very good point. As when we develop technology, I think we're collaboration with the industry partners here. We also realize that it's some of the workers are very conservative, and then they are worried about, say, I don't know, sensitivity, like privacy issue, and also get penalized later on. However, I believe technology itself is say you have to make the technology itself they perceive is useful, right? At the same time, it's easy for them to use and is for well-being of their well-beings. I think this one involves somewhat like a training and also enhance their awareness of the importance. And also, of course, technology-wise, we have to protect in their privacy so that they avoid their worries, right? So that's why I think at the beginning we do consider the different stakeholders like workers, safety manager, and then say the like project manager all together so that you ensure the technology we develop later on can be deployed. So here I do think about the very important thing for the like people or workers later on to accept it is training is very important, enhance their awareness. Another one is that I also think about the government regulation itself also very important because we have to build formal regulation. Say if PPE, you have to avoid when you're walking, for example, above 2 meters. So like this one, if you don't wear the helmet or harness or lifeline, you anyway we found it out and then remind you this is for you benefit, and then if you don't do it you will get penalized by the policy, right? Because if we have this kind of formal policy, I believe people will be able to accept such technology, because this technology, for example, is for PPE detection or for the 4 accidents. Once you have 4 accidents, well, we could save your life, right? So that's the same idea. I believe the change that mindset is very important, and then that they aware this is very important for their well-being, and of course resolving their concern, right? So that I think is great. So that is first one regarding to your comments. The second one, I think your suggestions for the putting the color tag on each of the joints, I believe it's very good point you mentioned about for like for example for the like joint detection. But for us, I think currently say for putting the tab on each of joints might not be very practical. And also when we build a data set, we believe currently the computer vision based technology already very robust. We found out that most of the technology we use to detect the joints, aside from high occluded cases, so they are pretty good, even though the night is very dark. So currently, I think computer vision has been significant advance in this field. So I think we don't need to worry too much about like which joints was detected accurately or not accurately. Currently, I think based if we use the right model and then have the data set which is large enough, we can get very good results based on my experience.
That was a great presentation. Thank you so much.
Yeah, thank you.
Thank you so much. Thank you, Salman. Thank you, Dr. Xiong. I'm going to Yibo. I think you had a question. Am I right?
Yes. Hello, Professor Xiong. I'm Yibo.
Oh, yes. Yeah, good to see you.
Very nice to see you again. I have a quick question, Professor. I'd like to ask your opinion, because in previous time we discussed about the sensor-based fall detection and the balance test. So, how would you compare sensor-based fall detection with computer vision-based fall detection, in terms of their advantages and disadvantages? Which approach do you think is better or is more suitable for construction sites?
Very good questions. Even we have both technology which is available from our map for fall detection. One is based on IMU sensor, wearable IMU sensor on the pelvis. Another one is that currently the computer vision based technology. I can say from industry perspective, they prefer computer vision based technology, because computer vision based technology itself is that sensor you have to attach each sensor for each subject, right? Each workers, which is very costly, and also workers doesn't like because wear something when they do the work, maybe causing some discomfort and also interference with their work activity. But computer vision, basically, you can say that there's no cause and also non-contactive, right? So basically the workers just do their daily activity or job activity without interference. So that is some of the like a good part for computer vision. However, I think a good part for sensor-based fault detection is that sensor-based fault detection, they can avoid the occlusion problem. Because sensor-based itself, they don't have, say, suffer from occlusion problem. Computer vision definitely, like for example, lighting conditions and occlusion, they will influence the accuracy. Even our model, we're trying to build like a robust model using like skeleton. So like skeleton with a person. So that is more robust. But still, if you have high occlusion, you can say the accuracy could drops, right? But the sensor-based, you say that's either your world sensor, that's detection is very accurate. So basically, I think in terms of the accuracy, in terms of occlusion, sensor-based fault detection is good. However, practically, the workers and the safety manager and also the for the construction side, like more practically, I think the computer vision based method is more like I think cost-wise acceptance from workers is more favorable.
Thank you. I understand. And I have following question is that do you have any plans or prospects to work with industry partner to introduce these very wonderful techniques to real construction sites?
Yeah, I think,
and,
thank you very much. Yes.
And are there any barriers to obstacle this process?
In fact, this project we are based on the collaboration with one of the industry partners in South Korea. I cannot share the name here because there are security issue. So we get the needs from them. So basically, for example, detection of PPE for prevention and detect for accidents, right? Happens. So that is some of the needs we get it from them, and then we collaboration with them. However, I do admit that the data set we had from construction side is still quite limited because basically you can say majority of the data what we get is still from the public data set. So for this kind of like a field data set, typically they don't willing to share with us, even though we collaboration with them. They want us to develop technology, and then later they finally tuning the model based on their own data set. They don't want to share the data because they have layout, facilities information. They don't want the others to know because those are the high tech, the factories. So that is some of the thing. Unfortunately, I found some difficulty to direct testing the technology we developed in different construction site. That is, in fact, I also look forward to open collaborations with our students, researchers, industry partners who are interested about those technology. I think definitely I will be very open for collaboration and testing in the future.
Oh, okay, I got that. Thank you, Professor Xiong. Thank you for your great presentation. We really learned a lot.
Thank you.
Yes, thank you so much. Haley, you're next. But before we go to that one, I have a comment from Sujan Akaria. A wonderful presentation and research for the first case of PPE usage detection. Did it also monitor for non-fall scenarios when a worker is working on a floor? They don't need a lanyard.
Oh, okay. So what? Could you repeat your question again? So if they're working on the same floor, they don't need
Sure.
9 yards. Yes.
Sure.
Yeah.
Sure. Did it also monitor for non-fall scenario? Parenthesis open. When a worker is working on floor, they don't need lanyard. Parenthesis closed.
Okay. So that is, I think, the reason you can say that, we don't, when we classify say, don't wear the helmet, don't wear the harness, or don't wear the lifeline or 9 yard. So we, at this moment, we didn't say they have to separate whether they are working in the same floor or working at a high level. So this system itself is mainly for the high level, like for example, above 2 meters. However, I think, the system-wise, if you have, say, the working the same level, you can, the manager itself, they can put in the specification. For example, this one, the cases in this case, the 9 yard is not necessary. So then in that sense, the algorithm, they will not output the alarm if the worker doesn't wear the 9 yard. So that is very easy. We give the option for the people to choose. For example, does this helmet is needed? Does this 9 yard is needed? that this how many is needed. So they just click yes or no. Then the system will run according to their specifications.
Sure. Thank you so much. Haley, please go ahead.
Yes. Thank you for a wonderful presentation, Dr. Xiong. I was gonna ask two questions from audience, but apparently one Dr. Ismaili asked from Mr. Sujan, and the another question is from Mr. Jorge. He said, considering some limitation of our industry, namely that it is a dynamic environment and that camera have constraints such as limited field of view when fixed. So how can challenges like multiple story buildings with different floors that occlude views or uneven surface faced by mobile robots be addressed to make the transition from research setup to actual implementation on job sites more feasible? So do you believe this transition will lead more frequent adoption on construction sites? And what time frame do you foresee this transformation? Was the question. It's actually uploaded in the comment section. If you want to read it one more time.
Okay. So let me take a look. Oh, there's several comments here. I think several questions have here. So I think you have what I mentioned about is that you mentioned about two part of questions, right? The first part of questions you mentioned is that the camera view, some of the they may not be able to cover the multiple construction site. That's true. So that's why I think single camera cannot be solving all the problems. So currently, I think if you look at most of the construction industry, like a need big company, they have several CCTV camera mounted. So in the different each of the side, each of the directions. So that's why I think the view side we have to ensure the input we can look at the construction side somewhat reasonably. Otherwise, the model will not work, right? Because if you cannot see it, then definitely you will not be able to pick the PPE compliance condition or the full accidents. So that's definitely I think we need multiple camera if we have multiple construction site. So that is hopefully answer your first questions. The second part of question you ask is about what? It's about the robot what's the
Yes,
questions?
when it's in uneven surfaces faced by mobile robots, how will this technique could be applied?
Okay. So mention about what you say that they have mobile robots and then they can
Yeah.
move around the different construction site. And then
Yes.
that's a good idea. I think you have very nice idea. Yes, that's true. We can have one single camera or few cameras which mounted on the mobile robot, and then that mobile robot just as a safety manager, they go around about different construction site, then do the monitoring. Yeah, I believe that is feasible. That's still is feasible. I believe that's a very good idea. For instead of mounted several CCTV camera, you can have one, but then it's just continuous moving around different construction site.
Okay, thank you so much. I really appreciate it, Dr. Xiong. Thank you so much for being the first speaker of this webinar series. We are going to have a YouTube channel, post all the recordings, and we really appreciate it. In order to keep it in the time limit, I know we have perhaps more questions from the audience, but because we want to keep it equal time for almost all of our seminars from now on. We really appreciate for your time and thank you so much for attendees. We will be in touch if you, and I ask our attendees, please follow us. We will have similar webinars with very interesting topics in future too. We have some of our speakers already scheduled, and we are going to share their flyers about the upcoming seminars. Please follow us and stay in touch. Thank you so much, Dr. Xiong. Really appreciated. Wonderful research. And thank you so much, audience. Have a wonderful day and weekend.
Thank you so much, Professor Pezet and also Ms. So for your nice arrangement. And thank you all again for attending the seminar and for the wonderful discussion suggestions. Have a nice weekend.
Thank you so much. You have a wonderful weekend too. Thank you so much, everyone. Really appreciate it. And Dr. Shuping, Yibo and I had some ideas. We will